Okay, I'll do that. No, see, it says record. It says recording in the upper left-hand corner. It's not asking me my permission. If you want an answer, yes, I give permission. I don't know about the other. There is a question in the chat, by the way. Maybe you can see it from Zhendong Liu.
Oh, it looks like that's a question for you. Let me make it bigger. No, I can't.
No, okay. What's the question?
It looks like head/phrase distinction is not made during syntactic merge.
Yeah.
Then how can this formalization of internal merge account for relativized minimality effect, where heads only compete with heads for movement, and so do phrases? And yeah, so you can answer the question whenever.
Okay, so about that, but then we'll try to get to just do that else.
I guess.
Okay. All right, so I guess today we're more online, but okay. So yeah, let me say something about this thing about the head. So yes, so in this setting, you have the merge that just really generates stuff, and of course, a lot of the stuff at the end of the day is non-viable in the sense that, for example, the head function doesn't work. So you have like exocentric construction that you cannot assign, a label, a head in a consistent way to. And those just die off in the next process. So the idea here is to kind of decouple a lot of things. So you decouple the generative process of merge itself that just runs on its own and doesn't check all these things. And then you kind of have different modules that take care of these different things. And for example, you get once you have all these freely generated syntactic objects that merge produces, including the movements that are done by internal merge, then among all of these, there will be some that will actually be compatible with things like feature checking and so on. But that, unlike what happens in stable minimalism, that you incorporate the feature checking in whether you can do certain kind of movements or not. Here you decouple the two, and then the feature checking comes after and then kind of kills off a lot of stuff that's not compatible with that. So this is kind of moved into this externalization part where a lot of things actually happen. So that too is like a multi-structured thing. One of the things that happen is the planarization of trees, the linearization of the linear ordering thing, and so all other kind of properties. Another is various other constraints from syntactic parameters that are language specific. And other things are these things about head, about data roles, and all these things. So this kind of decoupled from the generative process itself that just happens on its own and doesn't necessarily care about these things. So that's the picture. That's why I put this construction of head on some subdomain of the magma of syntactic objects and the subdomain that's not invariant with respect to the merge operation of the magma, because sometimes if you put things together, even if they separately have a well-defined head, when you try to merge them, you might end up with constructions that don't have the head. Okay, so I hope that kind of answers the question. Okay.
Thanks.
Yes?
Thanks. Yeah, also if I understand it correctly, is it also the part of the filtering mechanism in the externalization process? I mean, if I were to account for relativized minimality, is that also part of externalization requirements?
Sorry, can you say that again? Which thing is part of the externalization?
So this relative minimality effects. So do you think that is also the part of externalization?
Yeah.
Okay.
So and of course some of these things, like the head, for example, it also then plays a role in the interface with semantics that I'm gonna say in a moment. So in the sense, okay, the part of the things that happen, in this generalization part are actually tied up to what happens in the interface of semantics, although you can think of this as two different channels, but, of course, at many levels, they are interacting. Okay, so let me get back to what I was saying at the end of last time. So I was trying to explain this idea that the way that you want to make an assignment of semantic values to syntactic objects, you think of it as starting with some assignments of semantic values to lexical items, and then you try to extend that from lexical items to structures. And the way to try to extend it to structure is to do that inductively, of course, on the construction of the structures themselves, but do it inductively so that you incorporate in the way you assign these values some form of checking of consistency over substructures. And this is borrowing this type of construction from the way it's used in mathematical physics, and so we try to model it in a similar way. So what I was saying is that, in order to do a construction like this, the two ingredients that you need, one is entirely on the side of syntax. It is something that allows you to extract substructures and compare substructures with what is left once you remove that substructure. And this, we already know that the co-product of the algebra structure does exactly that for you. So this is, again, a place where you want to have this type of structure on organizing syntax. And the other thing is entirely on the side of whatever you want to put as your model of semantic space. And that what you want to have there is something that would allow you to, have some checking of agreement and disagreement, and so being able to distinguish between these. So, as I said, the first thing we already know algebraically what it means, what is the mathematical structure that takes care of that, is this decomposition operation, is the coproduct. And the second one is this thing that I want to start discussing at the end of last time, which is this notion of the Baxter algebra. So this is not very, it requires a bit of thinking to get the heuristic sense of what it means. So we have something so this is the original formulation of how it's used for the physics problem. We might slightly, modify it for the purposes of semantic parsing. But the basic idea is that you have some algebra. So an algebra is just the part of the Hopf algebra that only cares about multiplication, right? Not the co-multiplication. So you have a vector space, so that there's an addition, which is there's just a formal sum that you have in a vector space. But then there's also multiplication operation that has two inputs and one output. Okay. And on this algebra, you have a map which is not a morphism of algebra, it's just a linear map. And so if you can think of it really as a projection, so it's something that is idempotent, and it cuts off your vector space into two parts, the range of this map and the complement of that. But of course, if you just have a linear map that's important and does the splitting, a priori it has nothing to do with the algebra structure. So the two pieces that you break a vector space into, the multiplication doesn't preserve them in general. And you can ask, like, what is the minimal requirement that I can make on my linear map so that it will actually also break your space in a way that's compatible with multiplication? Of course, you can say if the map itself is a morphism of algebra map multiplication to multiplication, that happens. But that's kind of a strong statement. That's not always the case. But there's something that's a little less than requiring that, and that still has the effect that is split into an algebra into algebras. And this is the Baxter identity that I'm writing here. And this weight -1 that is written there is this -1 that's at the end of the identity, is minus R of AB. And you can have some weight lambda, where instead of -1 there you have like plus number. So you have plus one, the weight plus one would have a plot there, the weight zero will not have the last term of the weight. Okay. So there's one such structure for every lambda. So what does this mean? This looks a little bit strange. So the typical example that one has in mind of what such a thing is doing is something like this. Suppose that you have and write a formal sum of things. So I don't know, say some variables. And say. So I have some like formal sum of variables. Okay. I can give each of these variable a weight, so I can put them in some form like this with a polynomial. I'm just saying that I assign a different weight to each of these variables. Okay, so I make a polynomial out of that, so that it separates what each of those variables is, and it also gives me a way to multiply these things. Right? If I multiply two of them, I know that the degree k is a combination of the variables in the degrees, like the way you multiply polynomials. And so I can, if these are polynomials, let's know, but suppose that this starts out with some negative power. Okay. So you have something where k starts somewhere negative. So it's not a polynomial, it's a Laurent polynomial or Laurent series is very infinite many of them. Now when you multiply some of these, right? So you can say, okay, I have these things, and now what I want to project down to the part where I drop the negative part, and the part where I only keep the negative part. So, right, I mean, how do I think of this? I could think of this as being the part that when I set this variable equal to 0, it's giving me problems because it diverges. I'm dividing by 0, so I'm not doing a thing that's not so nice. And the part that instead has no problem when I evaluate it at 0, I'm happy with plugging in 0 here everywhere. And this is what physicists usually encounter, because they're going to have some terms that are badly behaved, that give divergences, that they are the things that have poles somewhere, and things that are nicely behaved. And so they say that your R is just the part that extracts what is bad, and the 1 minus R is the part that keeps what is good. Okay, and this strange identity comes from the fact that when you multiply two of these things, and you want to extract what are the negative terms, the negative terms are not coming only from the product of negative terms and negative terms. They can be positive terms that are not big enough to cancel the negative terms, and they will still give you negative terms. So this R is not mapping multiplication to multiplication, but it satisfies that identity. So that identity is the typical identity that happens when you try to filter out some bad things by degrees or something like that. So it's like some kind of threshold operation that you can change your threshold here. The threshold is set at 0, right? And that's a typical algebraic property that this type of filtering out operations satisfy. Okay, so but I'm going to come down to some explicit examples that are more relevant to the semantic parsing in linguistics. But this example is the original motivating one, because it's the one that shows up in the physics setting, and this one that motivated people to look at this type of algebraic structures. So, one thing we're going to do is modify this slightly, and instead of considering algebras or rings, we'll consider semi-rings. And of course, the fact that there's an interesting relation between syntax, between parsing and semi-rings in linguistics, it goes back to the work of Schutzenberger in 1963. This semi-ring parsing has been used after that a lot for various kind of, models of semi-ring parsing linguistics. So semi-rings is sort of what we expect to see as this type of target algebraic structure. So you can modify this Rothenbach thing by replacing algebra with semi-rings. I'm just gonna give a different, notation to the operations in a semi-ring with respect to the operation of an algebra, so that one can see that they are not exactly the same structure. The only difference that there is between an algebra, a ring and a semi-ring, I'm not making much distinction between a ring and an algebra. I mean, the only difference is that when you take formal sums, your coefficients are any integers, or they are, let's say real numbers, or they're in a ring or in a field. Okay, that's it. So I'm not making much distinction between the words ring and algebra here, but semi-ring, the main distinction is that the addition now does not have an inverse anymore. So what does that mean? It just means that, for example, if you take this formal linear combination, for example, if I say I only want to take formal linear combination where the coefficients are all positive, then of course it doesn't have an inverse because I cannot subtract anymore. So I want to subtract, I need negative as well as positive coefficients. So I can only add things, but I cannot subtract them anymore. And the rest of the structure remains the same. So the multiplication distributes on the addition, so everything is the same, except that my addition is no longer invertible. Okay. And this is in a sense good, right? Because it tells you that if you're I don't know, like looking at mapping in semi-ring, you don't have cancellation to worry about, because nothing can cancel. So that's the reason why in this parsing thing one prefers to work with semi-rings than with rings. So this is just one small change in the story. And the way it affects this identity is just the fact that the way I write it over there, I'm putting a minus sign somewhere. But if I'm in a semi-ring, the minus sign doesn't exist. So I have to move that term on the other side so that it has positive sign. And that's why I rewrite. Or I can consider the weight minus one instead of, the weight plus one instead of the weight minus one. So the only difference is I'm not allowed to write minus anymore. That's the only distinction. Okay, it's a very mild change. All right, so now how do these two things come together? So on the one hand, I have my syntax world, which has this Hopf algebra structure. At the other hand, I have my parsing, construction, whatever that's going to be, that I'm claiming has one of these Rothenbach structure. And these two are related by some map. Okay, so my map is going to be my parsing. So my map is going to be taking some elements of my Hopf algebra or syntax and sending it into this evaluation place. But how do I want to do that? I mean, what kind of properties do I want to require for this map? And so I'm just saying that the only requirement that I want to have is that it is a morphism of algebras, or if I'm semi-rings, it's a morphism from some sub-semi-ring of the Hopf algebra to a semi-ring, so morphism of semi-ring. So let's say more precisely what this means. Okay, linear combinations go to linear combinations. This is just a formal thing. Linear combinations are pure formality in all these matters, so they don't play any structural role. They are in order to describe combination of possibilities. So I just assume that those go to something of the same kind on the other side. So that's nothing. Other than that, I require that I have a multiplication. So on the source, I have two important things. I have this operation that puts together things, the multiplication, and I have the coproduct that tears them apart, right? So the things that put together things, remember that for us, it's the operation that assembles the workspaces. And it assembles the workspaces as these joint unions of syntactic objects. So if I have two syntactic objects that are there in the workspace, And they are, in different, so they are disjoint unions, so they don't overlap in any way. What I'm just saying is that whatever parsing I assign to one of them and whatever parsing I assign to the other, they are independent. Yeah, because there's no, a priori, they're just two elements of the workspace. I have not yet built any structures with them, so they can be independently parsed, okay? And so this requirement that this is a morphism of commutative algebras in the sense that it assigns independent evaluations to independent things that I have in the workspace, okay? So this is the only requirement that I make. So it's important that I'm not making any requirement about the coproduct structure. So I'm not saying that this map is compatible in any way with the coproduct structure. In fact, it's important that it's not. So I'm not trying to transfer the coproduct structure on the side of the target, on the side of semantics. This coproduct structure exists on the side of syntax, but I'm not in any way trying to rebuild a copy of it on the side of semantics. It will always stay only on the side of syntax. Okay. All right, so this is what I'm requiring for the map. And normally the terminology that mathematicians and physicists use is that a map that has this property, they call it a character of the Hopf algebra. A character with values in this particular Rotha-Baxter algebra that you've chosen as your target. Okay. So you're not transferring the same computational structure of the source, the Hopf algebra structure on the semantic side is an important point. Okay, so then if you have such a map, you can factorize it because the target splits into two parts by the existence of this Rotha-Baxter structure. And so if you have a map from H to this target, you want to use the fact that the target splits into two parts to split your map into two parts. And this is called the Birkhoff factorization of the map. And one can write it in a Hopf algebra term. This is the only place where this antipode map of the Hopf algebra enters, which is like inverting this one piece of the factorization. But one can also write it without appealing to this antipode map. It is 5 minus times that. These times, so the product, so these maps from H to R have a product structure, not so you can take products of these maps. And this is the reason for that is that one way of thinking about what a Hopf algebra is, of course, I gave you the formal definition with product, coproduct, and their formal properties and relations. But there's another way of thinking about what a Hopf algebra is, and it really is functions on a group. So if you know what the structure of a group is in mathematics, is just like groups of transformations or groups of symmetries, right? There's an operation, there's the composition of transformations in the group, and you require all of them to be invertible and to have a unit. And you require that the composition of these operations is associative. It might or might not be commutative. Okay, so that's an usual idea of a group. They come exactly from describing symmetries and groups of transformations. And if you take functions over a set, right? If I take functions over a set that have values in some ring or vector space or something, I can always multiply, them pointwise. Because I can just take at every point of the set the product of the values of the function. But if my set also has a group operation, then I also have a coproduct on the functions, which comes from composing with the operation of group. And that's actually one of the main sources of Hopf algebra. So functions on a set are an algebra. Functions on a group are a Hopf algebra. So this is just this product here of the maps is exactly the underlying group of which the Hopf algebra is functions, over which the Hopf algebra is functions. So this is a little seems a little complicated to say it this way, but no, what I'm really saying is that, okay, how do I multiply two of these characters of the Hopf algebra? I take the co-product of the Hopf algebra. Now this has two channels. I apply the first map to the first channel and the second map to the second channel. So there's actually in the end nothing. No, if you say as a general fact, it sounds difficult, but what it's actually saying is that you use the fact that you can turn an element into two outputs, and then you have two functions. You apply one of them to one output and the other to the other one. So it's actually this product is actually a very simple operation, in fact. Okay, so this is what the factorization means. You have a map and you want to split it into two parts. This product, it means that when you take a co-product in your algebra, this map is really one map acting on one side of the co-product and the other map acting on the other side. Okay. Okay, so why all these things? And because you can actually prove this is a mathematical fact that you can always construct one if I give you a character of my algebra, and this character has values in a Roth-Baxter algebra. So here is where you're using, okay, let me say this before showing what the actual construction is. I told you what I'm assuming about this map, about this character, is only that it has these, evaluates independent objects to independent things. So it has this multiplicative property, so the product of the algebra. But this map doesn't know anything about the fact that H also has a coproduct and that R also has this Roth-Baxter structure. It's ignoring both of them. But now I bring both of them in order to be able to split this map into two parts. So now where I'm using both the coproduct on this side and this projection, this Roth-Baxter projection on the other side, is in order to be able to split my map. The map itself doesn't know anything about this additional structure, but I can use them. I can use them to produce this kind of factorization. And of course, these two parts are, one is what is left when you subtract the other from the original map. So the amount of information that is contained you only need one of them to have the entire information about the splitting. Physicists attribute different meanings to these two parts. One of them they call the counter terms. They are like the divergences of quantity theory. The other are the renormalized values that are the actual physical values. But the information contained in one and the other is the same. So let's just look at one of them. So let's just look at the first one. So what you do is you take your original character phi, and instead of just projecting that, so the first term, this R of phi, would be you take your character phi and you just look at the projection on one side of your Roth-Baxter. It's like saying, for example, I look at this and I check whether it's okay or not, the value that I get. My R is a projection that checks, checks something. We're going to say in a moment what it checks in terms of parsing, but it checks if your value is okay or not with respect to some parsing property. So if I would just take R of phi of x, this would be taking the value that I am assigning to my structure. X is one of the structures that I have, and one of the syntactic structures in this case. And phi of x is the value that I'm assigning to that in my parsing. And R of phi of x is telling me, is this value okay or not? But I don't just want to say whether this value is okay or not. I want to say whether also all the substructures contained in that structure have an okay value or not. And so this is why I'm correcting this R of phi with a sequence of other terms. And the sequence of the other terms are coming from the non-trivial splitting in the coproduct. So they are exactly all the substructures that I can find inside X. And for each one of them, inductively, I'm applying the same construction to the extracted part. And so for each of the extracted part, I'm asking the same question. I'm asking, is this substructure assigned to a value in a good way or in a bad way? But this itself contains all the substructure, right? Because this is an inductive construction. So it's at each thing that I'm extracting, I'm asking the same question. And so I'm looking again at the substructure and so I'm packaging into a single thing all the checking of whether for each substructure, my assigned value is okay or is not okay. Okay. They all go into one checking, you know, of everything simultaneously. Okay. Yes.
I just want to make sure I'm understanding sort of the structure of
Yeah.
what we're setting up here. So we have our hooked algebra, which creates syntactic objects. And then we have these functions that map these objects into our semantic space, into our proto-vector space. And there are two functions that are doing that. And the functions themselves, if I'm understanding correctly, are not restrictive, right? Like they take any syntactic output and they always succeed at mapping it into one of these spaces. And then to the extent that there are semantic filters, they exist already at the level of checking the values in these different spaces.
Yes, so let me come to like a simple explicit example so that we can see exactly what all these things are doing.
Okay.
Which, yeah, so let me. So okay, there's the analogous was with semarines, everything is sort of working in the same way. So let me just take a very simple example. Right? What I'm doing in the parsing side is very simple-minded. But you know, let's try just to see what happens. And also we take an example of this you know, projection of the Rotobachster structure that is very simple. Okay, so let's take a semiring. So the kind of semiring that I'm looking at is what mathematicians call it's called either the max plus semiring or tropical semiring for strange reasons. And so it's real numbers. Okay, so I'm assigning a weight. That's a real number. It's like your value or also agreement. So agreement, disagreement with something. Let's say, I don't know if it's a large positive number. It's you have a lot of agreement with something. I'll say in a moment with what. And if you have like a large negative number, you have a lot of disagreement with something. If you have zero, is some neutral situation in which you have neither agreement nor disagreement. And you have a wildcard, which is this minus infinity value, which simply is there to say that certain things just cannot be evaluated. Like, for example, they don't have a good parsing. So then you throw them away by assigning them this minus infinity value. It's just, okay, this my test doesn't work on this one, so I throw it away. And the operation, the semiring operations are the max, as that's your addition. It's a non-invertible addition because math doesn't have an inverse. You take the maximum of two values. Okay, and the multiplication in the semiring is the usual addition. Okay, and so what is the Rotobachster structure? The Rotobachster operation is this type of ReLU threshold function that people who do machine learning are so fond of, right? If something has negative value, you kill it off, it's just zero. If something has positive value, it's what it is. So it's just the checking, so in this case, if we think of positive values and negative values as being agreement or disagreement with some hypothesis that I'm testing, if it's agreement, I keep it. If it's disagreement, I make it disappear. Let's set it to zero. Okay. So that's just, that's my checking. It's my, filtering out the bad guys. Okay. And so why is this a Rotobachster operator on this semi-ring of 21? So what is in this case the Rotobachster identity? Well, I write it out here because so max is our sum and plus is our multiplication. So the Rotobachster says the multiplication of two values of R, so multiplication of the two. So I write x plus for this max of x and 0. So multiplication meaning plus of the two thresholded things are the sum between max of the multiplication of this one. So these are the three terms of the Rotobachster identity in this case. So one just has to check that this identity holds. So you just look at all the possibilities, like when one of the arguments is positive, the other is negative, or both are positive, both are negative, whatever, and you see which one is maximal, and you just check that indeed this identity holds. So this is what we normally do, right? We check if something satisfies this Rottenmeister property or not. Okay, so it does. So I'm allowed to take this as my parsing, target. Okay. And all right, so now what I'm saying that I'm going to use this to be checking agreement or disagreement with some hypothesis. So let's assume that our semantic space is just some vector space. So again, I'm just doing some pretty dumb kind of semantics, but I just have some vector space, and I assign to, say, the lexical item some vector in this vector space, and I'm just using one of these usual things that evaluates how close by the vectors are to say how semantically related they are. Like one of these is pretty, not very sophisticated things. And so I can say, okay, I give you a vector that's your hypothesis, right? I want to see how much, what I'm evaluating agrees or does not agree with this hypothesis. Hypothesis is just one vector in my semantic space. And so I can test agreement by taking another vector and measuring how close it is to this vector. So I can measure this inner product in my vector space, and I can normalize. If I normalize it by the length, I get this cosine similarity that people are so fond of in computational linguistics. And okay, so I call these things a probe. So any vector I can choose is a probe with respect to which I can check agreement or disagreement. And now I do it in a very stupid way, right? So I do it like this. I assume that, so I take one of my syntactic objects. This is one of the generators of my algebra. So I take one of the syntactic objects. The first thing I check is whether it has a well-defined head or not. Okay, so I know already from what I said last time that some of them will admit a syntactic head and some will not. So if it does not have a syntactic head, I just throw it away as something that's non-parsable. And so I assign to it this -infinity wildcard that tells me this is bad. I don't want to deal with it. Okay. If it does have a syntactic head, then there's a leaf that is the head. Then I look at the vector. So that's now a lexical item. Right? So my lexical item are already mapped to my vector space. So I look at the vector where that goes. And I check how far that is from my probe hypothesis. And then I assign that as value. That now is a real number. A real number. Okay, so this is my very, very simple-minded parsing, example of parsing. Okay. Okay, if I do this very simple-minded, so I'm just, this is just what I'm doing. Like one of these, I pick one of these vectors, like this short one. This is my probe, and then I check the other vectors that come from the head of the where they are. Are they close by agreement? Are they orthogonal, neither agreement nor disagreement? Are they very opposite kind? Then disagreement. Okay. All right. Now I compute this. I do this Birkhoff factorization. So now this is giving me a character. Okay. That I have a character of my off algebra because I defined it on every syntactic object, and on a workspace, I know by assumption that the different terms in the workspace are evaluated independently, that it goes to the product of these ones, my construction of characters. So I have a character that I have constructed in this way. Now I apply this Birkhoff factorization with respect to this threshold as my Rottenmeister structure. So I throw this threshold is going to throw away anything on which I find a disagreement with my hypothesis. But it's not just throwing away whether the entire it's not just checking whether my entire syntactic object with its head is in agreement or disagreement with the probe. It's also checking on a sequence of sub, because of this recursive definition of this factorization, it's looking at chains of substructures that, so it's identifying for me the longest chains of substructures that will all maintain the agreement with the probe that I'm using. So this means that you are checking, right, where, if disagreement happens somewhere, you're checking where it's happening. And you're trying to identify the longest structures that maintain agreement. So here, I'm saying that this is a somewhat stupid way of doing this, because you're only using the position of the head. And so, of course, you know where it's going to happen, because if you follow the head, then you get the longest chain of things, because the agreement only depends on the head, right? So as long as you stay on where the head projects, so as long as you take the largest structure on which the head projects, then you're maintaining the agreement. So this is just telling you something very simple about how the syntactic head is working, and you don't get. So you, of course, you want to do something. This is like an example that what physicists will call the toy model example, in the sense that, okay, it illustrates some of the functioning of this algebraic machinery, but it doesn't give you a result that is very significant. Well, let's see, for example, let's see nonetheless, right, what it's actually giving you. For example, let's take a simple sentence, right? Cats chase small birds, no? And then your probe vector is your semantic vector in your semantic vector space that associated to the notion of predation, for example. Then, okay, chasing is close, cats, birds are either predators or prey, so they also have some relation to the concept of predation. And so if you look at all this chain of the substructures that you can extract from these three, the coproduct, you find that all of them have some agreements with this problem. So you get this long chain of things where everything is in agreement with this problem. But so this is like you extract, you have all the terms. For each one of them, you check, whether when you apply this threshold, it's above threshold or below threshold. So it has agreement or disagreement. You throw away anything that does not have agreement. Here you keep everything because there's some agreement with the probe. But for example, if I change the verb chase with something that's not, in a agreement relation with the concept of predator-prey, right? Predator-prey relation, then you would find that some of these terms now have a disagreement with the probe, and then they will be cut off by this threshold operation. And so it will tell you that some parts of the structures they will separate out which parts of the structure maintain an agreement with your probe and which part of the structure have lost an agreement with your probe. Okay, so that's how this functions. So of course I've chosen this example like in a very simple way, so that this simple thing of checking agreement using the head of the subtrees is giving you something. But it's easy to cook up an example where you can see that just following what the head does is not the right thing to do. For example, if I come back to the example that I was mentioning last time, France is a hexagonal republic, I find that in this case, of course, you can use the same idea that you take a probe, for example, the launch of government, and that will be okay with France as a republic, but it will not be okay with hexagonal republic because hexagonal doesn't have a high agreement with the notion of government. So, right. However, you don't see it in this case because you're only probing the head of each tree, and will not just probing the head will not see that in the structure that has hexagonal republic there is a problem. Okay. So, okay, so this suggests that maybe just following only where the lexical items go is which are all you need if you're only following the position of the head in your semantic space. Maybe just following where the lexical items go is not a good idea. No, you need to assign points in your semantic space, not just to lexical items, but directly to constructions themselves, to structures themselves, which are not only, so here we're just saying that the whole structure goes to wherever the head goes. But this is limiting, because you need something, you need the structure to go to something. Of course, it's related to where the head is located, but it's not just where the head is located. Okay. So this is a good excuse for introducing, the reason why I was saying that, if one type of way of thinking about, what properties you want to have on your models of semantic spaces can be thought of in terms of some kind of proximity relations, kind of topological metric type of, the relation that measure, in a sense, distances between things. Of course, I'm already using this because I was measuring, the distance between vectors in terms of their inner product, and this is already a kind of topological, has a consequence of being also a distance relation, a topological relation. But more generally, so one can assume that your model of semantic space is some kind of metric space. You have in mathematics one thinks of Riemannian manifolds or curved spaces that have a metric structure that allow you to evaluate distances, and where, for example, you can. The one important property you won't have is that if I give you 2 points on this space, there is a way of measuring the minimal distance to have a trace a curve between them, which is the shortest path between these 2 points. Okay, so these are called the geodesic arcs, and because there's a space that has this property is called geodesically convex, so you can always find the shortest path, the shortest way to go between 2 points. Okay, I'm always just going to write this out as a segment, even though if my space is curved, it would not really be a segment, but for simplicity, I'll just write it out as a segment. And so why I'm thinking of something like this, because this notion of having a shortest path between 2 points, it allows you to interpolate between 2 points. That I can find like an intermediate, an intermediate sequence of in between positions between 2 points. And so, for example, I can think of something like this, like if I give you 2 lexical items, alpha and beta, and I'm assembling them together into a structure, and I know that how to map, how to assign some kind of semantic points in my semantic space to the lexical items. I'm going to have, so this is inside my world of abstract, syntactic structures, but this is inside some semantic space. And so these points here have some path. That's the minimal, so the shortest path that interpolated between them. And I can try to say that, where do I want to map my entire structure is, well, it's somewhere between these two, because I can think that that's putting together these 2 lexical items is creating some structure that partakes of both by putting them in some kind of relation. Right? And so this is again a kind of naive model, but I can say, well, I will be somewhere, so my S of T will be somewhere here. And where do I want to put it? Do I want to be like, closer to here or closer to there, or it doesn't matter? So how do I want to think where I am on this path between these 2? Well, I can think of it this way. Again, let's use the head for something. So we know that either alpha or beta is the head of this tree. Okay. So let's say that the head of this tree is alpha. Okay. So that's kind of your, the head of your construction is the crucial word that you cannot remove without your construction falling apart. So I can think that, okay, that's the point where I am starting to do this modification along this path. And so I want to move move away from this point, which is the head of, where the head of my tree is located, and move somewhere down this path. And so, in a sense, how far do I want to move? Well, I think if that's where I want to compare, right? So suppose that, again, I have some kind of comparison function, which I'm writing here. Either is something that's, between 0 and 1, with like 1 meaning maximal agreement, 0 meaning no agreement, or something like this in a product that's real values, so I count disagreement and agreement. So something like that. And either way, I can say if my beta and my semantic values for beta and alpha have a lot of agreement between them, then I'm not moving very far away from where I'm not changing that much, where I am. So if these two have a lot of agreement, my point is not moving by much from where the head of the tree is. So pretty much it's saying that my earlier approximation, which is look only at where the head of the tree is going, is kind of okay. And this in fact agrees with the fact that in the examples that I was showing, if you choose your sentence so that all the words have already quite a bit of agreement with them, then following where the head goes, it's doing already a reasonably good job. But if there's a lot of disagreement between these two, then you actually want to move by a lot more, because then your modification is substantial. So you can just take that, and again, as I said, this is another pretty naive model, but you can just do that and assign points, as a combination. That's kind of a combination of where the two points go. And this combination is moving away from the head by a certain amount that depends on the amount of agreement of disagreement that you have with the endpoints. And now it's clear how to iterate that, right? Because if you have already constructed, so instead of lexical item here, you have already other structures, and you put them together to form a larger structure in your magma of syntactic objects. And if you have already inductively, decided where these two are going inside your semantic space, you again pick the shortest path between them. You know where the head of this is going to be the head of one or the head of the other. And depending on that, you decide how much you move away from the point that's, of the component that's contained in the head. So this gives you an inductive construction that maps your syntactic objects, well, those that admit a head, map them to point of your semantic space. And then you can again do this kind of thing of evaluating, how much agreement you have with the probe. You can also do, what I mentioned before about agreement with the probe in terms of inner product, it gives you a real number. So you are in this max plus semi-ring. You can also assign a probability of being closed, and then you have something that have values where you're doing a kind of probabilistic parsing. So the kind of semi-ring that you want in that case is this Viterbi semi-ring that has, instead of having real numbers with positive and negative meaning, it has probabilities between 0 and 1, And again, in this case, the addition is still the maximum, but the multiplication is the product of points between 0 and 1. And so this is another semi-ring that you can use, and then instead of this ReLU function that cuts off what is negative and that keeps what is positive, that you use for agreement, disagreement, in the example that I gave before. If you want to do this probabilistic kind of model, then your Rotabaxa structure is some threshold. So you cut off everything that has too low probability. So you set a scale and you say, okay, if something is less probable than this, I decide that it's an accident that I don't want to consider, so I throw it away. I don't only keep things that are sufficiently likely. So that's now my master structure. So I can do this. And, you know, then you get this character, then you construct a character in this way. It's kind of probabilistic assignments, you know, in computational linguistics, which value is with semi-ring. And again, if you do this Birkhoff factorization of this character, what it's doing for you is finding, again, chains of nested accessible terms where all of them carry a large semantic agreement between the constituent parts. And so they are all above threshold in this Viterbi scenario where your parsing lands. So again, you're like, you know, comparing with some probe if you want, and looking at the probability of them being, you know, related, being large or being sufficiently large or not. Or if you want, you're looking at all these, how much you're moving away at each step, and you wanna say that you maintain agreement. So all your movements or your displacements in semantic space are limited by some threshold. Okay, so it's the kind of things that this allows you to keep control of. So how many substructures you have that will, you know, be only, you know, minimal, or be not too much displaced from where you already are in syntactic space. So we remain in a small neighborhood of where you already are in semantic space. Yes.
So I think my question is just clarifying that point, really.
Mhm.
So I think at the beginning, when we started talking about this, I wasn't thinking necessarily about what the co-product is giving the semantics to look at. Are you saying that it's all of the accessible terms that are receiving a mapping into the semantics, or we're just looking locally at every binary branching node and assigning semantic values and evaluating for each one?
Yeah, so what is happening here, right? So we pick, so you pick one syntactic object that you want to try to look at, you know, not just so you take one syntactic object, and this one has it corresponds to, you have constructed by some way by using some kind of notion of agreement and disagreement, or probabilistic, or so, where you're mapping it to some point in semantic space. But now you wanna check, right, what is happening to overall the substructures of this same syntactic object. And you wanna say whether some of these substructures have, you know, so is everything staying? So this, you know, I am somewhere, you know, in this space, right? And so I have like I have a notion of proximity in this space. So I can say, are all my substructions staying in the proximity of where the entire structure is mapped, or are some of them like very far away? Is there some kind of you know, mismatch where, you know, some substructures are all concentrated, you know, in the same area, but some are kind of off, or not. So this is.
Are all the accessible terms, or just?
Yeah, exactly. So you are looking at the things that, because you're using your coproduct, you're extracting all the accessible terms. And so for each chain of extractions of accessible terms, you're checking whether that entire chain is staying in a neighborhood, in the same neighborhood in your semantic space or not. So you can see whether at some point there's something that's off. And so, you know, that takes care of these examples, like the example of Republic, right? Because so let's if I look at that, so this if you want, it's enough to take a subring of this Viterbi semi-ring, where you only have, instead of values between probability between 0 and 1, you have just 0 or 1, like agreement, okay or not okay. No, is this, no, good or not? And for example, let's look at what happens in this specific case. So your France is a hexagonal republic is this syntactic object, right? And I'm extracting all the accessible terms through the coproduct. Now, of course, because you have only values zeros and one, the only threshold that you have is the identity. You don't have enough room in between to put other thresholds. So your Rotobaster is just the identity. So what you're doing is you have the list of what is on the left side of the coproduct and what is on the other side of the coproduct multiplied. And now you see that, some of these things have consistent parsing. So you see these subtrees that correspond to France is hexagonal and France is a republic. Those get a value 1. So those terms stay. But then you get these ones where you extract hexagonal republic as a term that gets value 0. So that gets killed off. So it's kind of separating out where the substructures are consistent and where they're not. And of course, if you have like some in-between values, right, not just 0 and 1, which tell you like what is the likelihood that these two things go together, then you can say, I like put everything to 0 when the value is too low, and I put everything to 1 when the value is sufficiently high. And that's your threshold Rotobaster structure. So you can decide where you set the threshold in between 0 and 1.
So just to make sure I'm following that, I guess France is a republic versus France is a hexagonal republic. Should those give different total values?
Right, so here, right, what happens is like, so if you have France, hexagonal republic, right, you get these two. So the first one is just the entire thing itself, and you can say the entire thing itself sounds strange, so it's not a good thing. So that goes I decided it has value 0 because I don't like this parsing that this semantically doesn't sound okay. What about the second term? Okay, then this one is hexagonal republic. So this is again something that has a term that's problematic. So okay, that goes. But then you have these terms that just have is hexagonal or is a republic. These ones are okay. Right? So these terms stay. And then okay, you have the other ones, where again you have some of them that contain this bad pair, hexagonal republic, and some that don't. And so those ones are the ones that are marked as bad, and the other ones are the ones that are marked as good. And so this is splitting out. It's sort of identified in each substructure which ones contain the problem and which ones get around the problem.
Good. But once you filter out all of the problematic terms, aren't you left essentially with the
Right, so this
value
is
of France as a
yeah,
republic?
so exactly, this is telling you that the maximal substructures that are okay in this case are the ones where you take only France is hexagonal or only France is a republic, and those are the only maximal substructures that where you can get a good parsing.
So I guess maybe what I'm missing is what accounts for the judgment. So if the semantic value, so if you're always allowed to just delete all the zeros, my intuition says that the semantic value assigned to France as a hexagonal republic is going to be equivalent to France as a republic. And so the question is, if they're both getting the same value, if they're both being scored the same, why is one of them judged weird? Is it because there was a word in it that didn't contribute to the value, or what is the filter, I guess?
Yeah, so in a sense, if I understand your question correctly, what contributes to values in a sense, what type of probe you are checking these things against, right? So, it's what you use to decide that this thing is okay or not. Like, for example, in the other example that I made, like, cats, as I said, okay, my probe is, predatory behavior, whatever. So these things are match or don't match according to the probe that I'm making. Here, I could say, like, if my probe is governance, or my probe is Yeah, okay, I can repackage this example, for example, let's separate out the two things that work. The France is a republic and the France is hexagonal. So I can further separate them out, for example, by saying I take as probe governance, okay? So now, this France is a republic is in good agreement with that. And France is hexagonal is not a property of governance, so I drop that would make me drop the other one. Or if I decide, that's something about geography, shape of geographic, whatever, you get a semantic probe that would detect, shape of territory, whatever the shape of the territory would be, then the hexagonal would match and the republic would not.
So Matilda, I think just drill down into that a little bit more.
Yeah.
Maybe, I don't know. I think maybe you're looking for, why is it that the topmost one turns out to be 0? Given that you have these two below where there's 1. I mean, so it's this image of a computational, again, a computational process that's coming from the bottom up. It has 1 here, but then you arrive at 0. And that's a quote explanation. What? So is that what's coming out of here or not?
Yeah, that's right. So the point of this is that, what you are comparing, so the top one is going to be constructed according to this type of construction, right? So if I am, the point is, if I have two things that are not in agreement, that my point, where I place my point, is very far from where I put it as far as possible, like from where the root of where the head of my tree is going. And so if I have a probe that's okay with the head of the tree, it's not going to be okay with the move that's moving back. So that's why the larger thing is not, in agreement with the part that's okay but it's being displaced. Yeah.
So I guess one way of thinking about it is the semantic value that you're assigning to some substructure is not just an absolute thing, it's always relativized to the probe that you're looking at. And so if you're getting to a value from one probe that you wouldn't get to from the other probe, and the disagreement.
Yeah, so this is the value of the larger structure is not directly, so it is determined by the values of the smaller structure, but through this kind of geometric displacement inside your semantic space, but sort of moving away from the interpolating between the points where your substructures are in a way in which the displacement is somehow proportional to the disagreement that there is between the substructures. Yeah.
Thank you.
Okay. All right, so in particular, let's see where we are. All right. In particular, this kind of construction that I illustrating here is even with this very, very simple naive idea of what to put on your semantic space, which is only this notion of proximity and interpolation. It's creating an image, is creating an image of your syntactic objects inside your semantic space. Because, for example, here, right, you can think of this segment with this point marked on it as an image of this tree, or this binary rooted trees inside of S. And if I'm looking at another structure like this one, and I know where these points are going in my schema, and with all the two like this. Okay. So I've done this one first, so I'll say alpha beta, and then let's say I make another merge with the gamma. Okay, so I have now these things, and now I have like another path, and I'm gonna be somewhere on this path. And I can see that this is an image, inside my semantic space of the syntactic object of the tree, the actual topological shape of this syntactic object. So this is this very even just this very naive way of using interpolation by these geodesic arcs in my semantic space produces for me an image of syntax embedded inside semantics. Okay. And then there's a reason why I'm sort of presenting this, even though it's a very simple-minded idea of what my semantic space looks like. But it's because, I'll come to talk about that tomorrow, that the things that we are seeing now happening, like these large language models and all this kind of stuff, what they are really dealing with is simply this fact that, whatever stupid model of semantics one is using, like these vector spaces that they're all so crazy about, it carries inside itself an embedded copy of syntax. And what we are actually doing is the reconstruction, the very computationally hard inverse problem of reconstructing syntax with its computational process from this very vague image that syntax produces of itself inside semantics. And this is something that I will talk about much more tomorrow. But so this is the thing you get. But so there is something else before we get to that type of stuff. There is something else that we could do about using just this, again, this very simple-minded idea that I explained here, which is to get a simple geometric model of how these two channels, externalization and this interface with semantics, interact with each other. So in the way that we've seen this so far, okay, you have this free symmetric merge mechanism that's just computing these syntactic objects in a kind of arbitrary way. You have lexical items at the leaves, and you have non-planar abstract binary rooted trees. And then on the one hand, you go down this externalization procedure, and you end up with a language-dependent choice of planarization, of linear ordering on these trees. And so when you go down that path, one thing that you're taking care of or keeping track of is the fact that you have all these different choices of planar structures on the same underlying symmetric free product of the free symmetric merge. And on the other hand, you can go down the other side and map to some simple-minded model of semantic space that has this type of topological property, like vector spaces do, for example, but other things as well. And then what you're doing here is you're introducing some kind of metric structure, because now you have picked certain lengths on these segments when you decide where you play. And those lengths of those segments depend on some kind of notion of proximity, of like whatever people wanna use in this case. And so here you have this metric type of information, and on the other side you have these planar structures type of information. So this diagram, when you wanna combine these two things together, you want to combine them in some place that takes into account both things, the different choices of planarizations and this type of metric information. So what are these places where they do all this type of stuff for you? So mathematicians have these kind of spaces that have been used quite a lot to study binary rooted trees with various kind of structures. So everything is already in place. You just have to fish it out and use it. So the thing that keeps track of all the different possible planarizations of an abstract binary rooted tree is a geometric object that is called the associahedron in mathematics. I'll tell you in a moment what it is. Okay. So this is the place that's designed to take into account the different choices of planarization and how to go between one and the other. If you think of your externalization that assigns planar order as something that depends, for example, on word order parameters of different languages, when you compare, the different word order structure of different languages, you are moving along this associahedron, inside this associahedron space by some transformation, by some symmetries. So you can think of comparing different syntactic parameters of different languages as being, geometrically realized by some symmetries of this associahedron space. I'll say something more in a moment. And on the other hand, as we're saying here, the hierarchical structures that are produced by the pre-symmetric merge acquire some metric data when you map them inside semantic space in this way. And so you need another place that parameterizes for you the choices of metric data on an abstract binary rooted tree that's not been planarized yet. And there is another such space that mathematicians use, which is called the BHD modular space. I will tell you what that is as well. That does exactly that. So it takes into account different choices of metric structures on abstract, non-planar binary rooted trees. And these two things they are apparently different because the associahedron doesn't care about the metric structure, and this BHB modular space doesn't care about the planar structure, like these channels of the externalization and map into semantics. But these two spaces are actually coexist inside another well-known mathematical space, which has actually been originally constructed for a completely different purpose in algebraic geometry to study, real algebraic curves. It's called the modular space of real algebraic curves of genus 0 with marked points, which doesn't say much, but it's called that way because that's the kind of object that it was originally designed to describe. But it turns out that it really is the place that puts together these two structures in the same place. And this is the picture that I'm going to talk about. I think this is I'm kind of coming close to the end of the lecture today. So I will start to say a few words, but then I will finish describing it tomorrow. The associahedra are where you choose this planar structure and you move between one planar structure and the other. And this BHD modular spaces where you keep track of this symmetric information, and the combined space is where you do both things at the same time and in a consistent, compatible way. And that's where you do externalization and this kind of semantic parsing in simultaneous in a way that's then guaranteed to be compatible with each other. So let me just start before we have to finish today by telling you what one of these two things is. What is this associahedron that parameterizes the choice of planar structures on an abstract tree. So if I have an abstract tree, binary rooted tree with n leaves, then this associahedron is some convex, it's like a polytope, so it's a regular, so kind of the analog of a polygon or a polyhedron in higher dimension of dimension n minus 2. So, for example, if you have three leaves, you have only two possibilities of planar structures. Right? For three leaves, you have this one, and you have this one. So this is these are the bracketing this way and bracketing this way. And so in this case, the associahedron is a one-dimensional thing that tells you that you have this. You have only two possibilities, so you have two vertices, and you have an edge between them. An edge means one of these switches of bracketing that corresponds to one associativity relation that you need to do in order to pass from one to the other. As saying, if you say, if this were an associative relation, then this would be equal to that. It's not associative, I have to do one change of bracketing to go from one to the other. And so I put an edge whenever I have to do one such change of bracketing. So in the case of 3 leaves, that's all I have. There's nothing else. In the case of 4 leaves, one can check that you actually have a pentagon where you have 5 possibilities, and they are related to two of them at a time are related by one of these changes of bracketing. And if you have that in the case of 5 leaves, then you have a 3-dimensional structure, which you can see from the back and the front like this. Each of the pentagon is like one of the 4-dimensional cases, or one of the things remains. So you have this kind of structures, and you have one for any n. So any number of leaves will give rise to this way of mapping all the possible choice of planar structure and which one are close to one another, in the sense of which one differ from one another simply by one simple change of bracketing. So in that sense, like, for example, what I was saying about comparing different word order structures, right? You can say, for example, you can check where the corresponding word order for Syntactic differ, whether they differ by a lot of these changes, whether they are very far away from each other on these as vertices of this associator, or whether they're very nearby, something like this. It's a place where you can compare different planarization and have a way to say if they are close to each other or they're not close to each other. And now, I mean, you can say also that you can fill in like this. So here I've only given you the vertices and the edges. But you can sort of fill in the faces, for example, by these 2-dimensional faces. What does that mean? Because now I have some continuous parameters on these faces, and that you can think of as incorporating some metric information. So you can put some coordinates right on for example, if you have 4 leaves, you can say that these 2 internal edges are. Well, one of them is very long and one of them is very short. So the reason for doing this is that, for example, when you want to pass from one type of tree to another type of tree, you can say that one of these edges become of length 0, and then it becomes like again, but in a different position. So if I want to pass, like, if you look at it, if I shrink this edge on the right down to 0, then I can pass one of the two edges to the other side and make it okay. So I'm kind of decomposing my I get for each. So each vertex of this pentagon is one of the possible bracketings and one of the possible planar structure. What it means that I'm going from one to the other, it means that I'm shrinking one of the edges to 0, then I'm reconstructing it again, but in a different position. So that corresponds to having done the switch of bracketing. So I get this way of parameterizing the actual interior of this associator. And what about the other thing that I mentioned? What's happening? Okay, I have to stop. Let me just say this as the last thing. The other thing that I mentioned is where I'm not choosing a planar structure of the tree, and I'm only assigning some metric data to the edges of the tree. And this is this BHV, Millera-Workman moduli space of metric trees, where you have now the thing to do is, which you don't do in the associator, like if you look at here in the associator, you keep the ordering of labeling. Now these are planar, right? So you keep the ordering of labeling as a string fixed, and you look at the different bracketing of this thing. So you're not permuting the labels. You're keeping the thing and you're changing the structure, but the tree is planar and it's linearized. So this is after linearization, okay? It's the different, planar tree structure that correspond to the same linear ordering of the leaves. And here instead, you don't do that. You actually your trees are non-planar, and you can permute how you assign the leaves, the labels to the leaves. And so you get the different tree structures, which now you see they're all hanging. So you have only three possible tree structures in the case of tree leaves that are binary rooted, and they only differ by the permutation of the labels on the leaves. Yes.
There is a question on Zoom. There is a question on Zoom.
Okay. Oh, sorry. Yeah.
Hi.
Yes.
I'm Kurosh. I just wanted to ask, now when you go to planar trees, do you still have a Hopf algebra structure there? And if yes, I remember that when you go from planar binary trees, you can take the Knut correspondence to go to planar rooted trees in the sense of just arbitrary rooted trees. And would this make a big change in the way of understanding how the trees are sort of involved in this linguistic picture? So I'm not a linguist, so
I talked a bit about this different situation that you have when you do this theory of linguistics with the planar, starting with the trees already planarized, right? And then this kind of this older version of minimalism where your trees are already planarized, and moreover you don't use forest, you're only using trees. So then you have to use this kind of Lode-Ronkov algebra of rooted trees. And so the Hopf algebra structure changes completely in that case. But here I'm still thinking about the fact that my Hopf algebra is coming from just these non-planar trees. So my Hopf algebra and with forest, right? So this Hopf algebra is just the one that, so the coalgebra structure is the one that's coming from, well, either depending on whether we want to keep this what we call this trace or not, is either the one that's the accessible cuts, or is the one that's like the Feynman diagram, so you contract the trees as Feynman diagrams in contract. But so the Hopf algebra is unchanged. But this is happening like after. So the Hopf algebra is taking care of your generative, where you generate your syntactic objects, and this is happening after that. So at this point, you're either planarizing the trees, but then no longer doing this merge operation after that, or you're mapping them to, you're adding some metric structure to the non-planar trees, and then you want to combine these two things. But at this point, in some sense, the computational part, that uses the Hopf algebra has already happened with the non-planar trees. I don't know if this answers.
Okay. Yes. May I ask one more question? It's related to the different semirings, if I understand correctly, in the different Rota-Baxter structures you mentioned. Can I understand then that was there a choice? Maybe I couldn't follow that fast. So is there a choice in this different semirings and the different Rota-Baxter structures? And if yes, would it make sense to ask what would be sort of a change of scheme, so to say, change of this subtraction type scheme?
Yeah, yes. So this is exactly like, in physics, you have a choice of a regularization scheme, right? Like whether you do dimensional regularization and minimal subtraction or something. And so your choice of Rota-Baxter structure in physics corresponds to the choice of a regularization before you renormalize. Then the Birkhoff factorization does the renormalization with respect to that regularization scheme. So here, in a sense, it's similar, and the point is exactly that, yeah, this is a very good question, because, you know, it's exactly why we're, in a sense, taking this point of view, because, you know, there are many different models of semantics, you know. And in a sense, you would like to construct a model of the interface between syntax and semantics, which is as much as possible agnostic with respect to which model of semantics you want to use. And in order to do that, you can kind of think of different models of semantics as being like different regularization schemes for the physicists, in which the same mechanism applies, and it applies with changing your target Rota-Baxter structure in various ways. But you're still kind of following the same mechanism, which is takes into account this compositionality requirement that you want to have about syntactic parsing. But it allows you to remain sort of agnostic about exactly which model of semantics you wanna use. And so it allows you to incorporate whatever, I mean, these vector space things or others where maybe your target is some class of functions, you know, or so it makes it more flexible to, you know, be able to incorporate different type of ideas of semantic parsing, you know, that, yeah, would be like the different regularization schemes for physics.
Thanks.
Okay, so I think I should stop here for today. Okay. Thank you. Yeah. Okay, is there any other questions? I didn't see if there's. Okay. All right, thank you.